Alrighty, so in this video, we're going to look at differentiation from first principles. So the first thing I would say is if you haven't covered differentiation yet in maths, do not bother watching this video. It will make no sense to you and just be a complete waste of your time. But what we're going to do is use the material that I looked at last in my previous video about what a gradient is and how we calculate it. And I'm going to use that to show you how we can find the equation of a gradient of a graph at any point, as long as we know the equation of that graph. And that is the process called differentiation. So the first thing I want to do is ask you a couple of questions to see where your initial knowledge is at. So if you want to grab yourself a scrap piece of paper so you can write these down. So first thing is, when you find the derivative of an equation, what are you actually finding? And the second thing I'd like to ask you is, what are the derivatives of the following terms, to see if you can actually apply the rules of differentiation before we show you where those rules have come from. Okay, so I'm going to assume you've done that. So let's talk about these things before we get into differentiation from first principles. So what are you actually finding? You are finding the equation of the gradient of your line, or let's put in of your graph at any given point. So this doesn't generate a number necessarily, it will generate an equation that describes the gradient of your graph, or the gradient of a tangent to your graph at a particular or point that you might be interested in. So we can use that equation to describe maybe how the gradient will change and stuff like that. So hopefully when we're learning differentiation, you have essentially learned the following rules. When you differentiate something, the index, or the power, if you like, should come down by 1, and the old index then gets moved to the front. So here, the derivative, which we usually express as dy dx, will be 2x to the power of 1, which is just 2x. So you take the index down, or the power down by 1, so it goes from 2 down to 1, and then the old power multiplies out the front. So we can apply that rule to the following. That's just going to be 3x squared. Anyway, this one looks confusing, but if we actually follow the same rules, it still works. It just becomes minus 2x to the minus 3, which is actually another way of writing minus 2 divided by x cubed, because this number here is basically 1 over x squared. So we're just using the same rule for all of them. You take the old power and multiply it out the front, and you subtract 1 from the old power as well. So that's what we do when we're differentiating to find an equation. But where does that actually come from? Like, how do we get that number? So that's what the main focus of this video is. So the first thing is, how do we find the gradient at a point on a non-linear line? So that just means a curved line. Well, if we want to find the gradient at a point, what we do is we draw a tangent and find the gradient of that. So you can see, if I want to know the gradient at this point here, we draw a tangent to the line at that point, and we find the gradient of that tangent. So the gradient at that point would be change in y over change in x. That's our general way of doing it. But that doesn't help us get to the results you've seen so far. So we're actually going to take a slightly different approach. What we're going to do is actually find the gradient of some chords. So a chord is a line that joins 2 points on a curved line. Most commonly you come across them with circles. So you can see here, I've shown you what a few chords look like. So we might have a chord that goes from here to here, so it joins those 2 points. We might have a shorter chord that goes between these 2 points here. And what we're going to do is we're going to use the fact that the closer the 2 points we draw the chord between get, the closer the chord gradient becomes to the tangent gradient. And we're going to see what happens to the equation of the gradient of the chord as the length of the chord tends towards 0. because when the chord length is 0, the grade, so let's actually add that in there. So when the chord length is 0, it will have the same gradient as the tangent, is the key idea that we're using here. So the reason we do it with chords is we can, if we know the equation of the line, we can actually describe those 2 points and we can find out what that gradient is. And then we'll see what happens as we make our chord shorter and shorter. But that's the general process that we're going to go through. Okay, so let's take a simple example first. We have a line with the equation y equals x squared. So that should look like this. And what we're going to do is we're going to pick 2 points on the graph, but we're going to label them in a special way. We're going to call one point has the x coordinate x, which means it has the y coordinate x squared, because it's a y equals x squared graph. And we're going to pick another point which is slightly bigger than x. So we're going to add to it this term dx, which dx is going to essentially stand for the number we're adding to x, which means this point here will be x plus dx squared, because it's still a graph of y equals x squared. And so remember, the gradient is the change in y divided by the change in x. So let's actually do that. So the change in y is going to be x plus dx squared. That's the y coordinate furthest to the right. And we're going to subtract from it the initial y coordinate, which is just x squared. And the change in x, I almost cut through my stuff. Let's make that a bit neater. Change in x is going to be x plus dx, which is our furthest to the right, minus x. So you should hopefully spot straight away that on the bottom line, that and that going to cancel out and just leave you with dx. And what we're going to do is actually multiply out the top line, because we can see the x squared term is going to get subtracted and cancelled as well. So we're going to do x squared plus what we're going to get 2x dx, and we're going to get plus dx squared, and we're going to subtract from that x squared, and that's out now all over dx because those x's cancelled. We should now spot we've got some more cancellation, so that cancels with that. And we can also now divide through by dx, because both of these terms have a dx. So we're going to get 2x plus dx. Okay, so our gradient can be described using this. So what we said earlier is we're going to see what happens to the equation of our gradient as our chord gets shorter and shorter. So what that means is what happens as dx heads towards 0. Because to make our chord shorter and shorter, that means dx is going to become a smaller and smaller number. So we ask ourselves, well, what happens if dx heads towards 0? Well, what that means is the gradient is going to head towards 2x, because this number here is going to head towards 0. There. So what we've got here now is an equation of our gradient, or an equation of our tangent at that point, which you'll notice is the derivative, because you can see x squared has become 2x. So this is how that process is essentially working. So let's repeat that for a different graph so we can actually see it in action again. So this time we're going to do it for a y equals x cubed graph, and the positive of that looks kind of like the x squared one, so we're not going to do too much. So this time our y coordinates are going to be x cubed and x plus dx cubed, but otherwise you can see our setup is pretty much the same. So let's do it. So we're going to do x plus dx cubed minus x cubed, and we're going to get x plus dx minus x. So you can see straight away we're going to get the same thing happening here. And what we're going to do is, just like before, we're going to multiply them out. This takes a bit more work. So we're going to get x cubed plus 3x squared dx plus 3x dx squared plus dx cubed minus x cubed all over dx. You'll notice again that these all cancel out, and we can see here we can divide through again by dx. We're going to get 3x squared plus 3x dx plus dx squared if we divide through everything by dx. So we're going to do the same thing. So as dx heads towards 0, what's going to happen? Well, that heads towards 0. That also heads towards 0. So you can see that just becomes 3x squared, which you'll notice is the derivative of x cubed. It does become 3x squared. So you can see our method works. Now I want to show you this again for our final equation that we started off with, but you can see it becomes a lot more complicated if we start using more annoying functions like y equals x to the minus 2. But the key is the process is exactly the same. We take a point, x, with its y coordinate, in this case 1 over x squared. We take a point x plus dx, and 1 over x plus dx squared. And we find the change in y divided by the change in x. Here it requires a bit more working because we have to combine these two terms together by giving them a common denominator, which is what you can see happening from here to here. I've given it a common denominator of x squared, x plus dx squared. And then I've worked through, and you can then, but then we do the same thing. Once we get to this result, we go, well, okay, what happens as dx heads towards 0? So that term heads towards 0, that term heads towards 0, and you end up with this expression, minus 2x over x to the 4, which becomes minus 2 over x to the 3, which is another way of writing minus 2x to the minus 3, which is the derivative of x to the minus 2. So you can see what we're doing is we're finding, in our case, we're finding the gradient of the chord, but as dx heads towards 0, that becomes the gradient of the tangent. So essentially, differentiation is finding the equation of the tangent, or the gradient, if you like, of our graph. Okay, so what I'd like you to do to finish off, we've been through the process a few times. I'd like you to describe to me the key principles used to determine the equation of the gradient of a line of best fit, which has a known equation. So take a few moments, pause the video. I'd like you to write out what are the key principles that we've used in this video here to determine the gradient of our line of best fit, or the equation of the gradient of line of best fit. Okay, so our first stage is pick 2 points on the line of best fit. So I'm going to say our equation with, let's do with the x coordinates first of all. X coordinates, then it's x and x plus dx. Determine the y coordinates, those 2 points using the equation of your graph. So that might be x squared, x cubed, x to the minus 2. It doesn't matter what it is. It would work even with logs and exponentials as well. Still works. Calculate change in y divided by the change in x. That's your gradient. Find out what the equation becomes as dx tends towards 0. And that's our final stage there. And that will give us the equation of the tangent to our graph at a particular point on the graph. And that's where we'll leave off this video differentiation from first principles.